Right, so we went through all of this and we are on to part E of the question. It says that, part D, number 3 of part D, it says if the spring was stretched beyond its elastic limit, how would this affect the shape of the graph? And that's 1 mark. So you just need to just write a simple statement. Now remember that we said that for Hooke's law, the relationship between the force and the extension is one of direct proportion. However, Hooke's law is not obeyed outside of the elastic limit. So if there is excess force that is placed on the spring, then you're not going to have proportionality anymore. So it means that instead of having a straight line all throughout, you're going to end up with a curved portion at the top to show that the relationship is no longer one of proportion. Right? So generally, when we draw straight line graphs, it shows proportion. If it is a straight line graph from the origin, then it shows direct proportion. Once you have a curve, then the relationship is not proportional. All right? So just that simple statement. All right, is that clear?
Yes.
All right, then finally, it says, how would you identify the region where proportionality exists? We kind of just touched on that a while ago. You said that once you have a straight line, it shows that you have proportion. All right, so you just write that. You would have proportionality would exist at the area where you have a straight line in the graph. So these questions are pretty lengthy because it's 25 marks for the data analysis question. The rest of the questions are 15 marks each, so they are not as long. All right. Are there any questions before we move on?
No, miss.
All right. So the next topic that we're going to be moving on to then is turning forces, or what we call moments. All right. Now, according to the syllabus, you should be able to define what the moment of a force is. And we have over here that the moment of a force is basically the turning effect of that force, or what we call torque. So there are some times when you apply a force to an object, especially if the object is pivoted somewhere. If you apply a force on either side of the pivot, then the object is going to turn either clockwise or anti-clockwise. So we calculate moments by multiplying the force, the magnitude of the force in newtons, by the perpendicular distance from the pivot. All right. So if I can just draw a little blank. So remember that, just to say that we have a piece of board here. If it is pivoted here and we apply a force downward, then you could say therefore that the plank would turn in an anti-clockwise manner, right? So it would turn anti-clockwise. If you're doing an exam and you're not sure how to identify the clockwise or anti-clockwise forces, you can use your pen and use your forefinger and your thumb to kind of act as the pivot, and then you can swing the pen on either side with the force, and then it will help you to see or to visualize whether you have a clockwise force or an anti-clockwise force. Or generally, you can say if it's to the left of the pivot and it's a downward force, then it would be anti-clockwise. If it is to the right of the pivot and a downward force, then this would be clockwise. All right. Now, if this force has a magnitude F, to calculate the moment of the force, we multiply the magnitude of the force itself times the perpendicular distance from the pivot, right? Now we say perpendicular distance because if you look at the force is acting in a vertical manner, but the distance that we measure is a perpendicular distance. So you see the red angle is here, right? Now the SI unit for moment is Newton meter, all right? We measure forces in newtons, and the SI unit of distance is meters. Combine the two, we get Newton meter. Now, it is also important for you to be able to state the principle of moments and to use the principle of moments to solve problems. Right now, basically, if an object is in equilibrium, then it means that if you add up all of the anti-clockwise moments around a point and you add up the clockwise moments about the same point, they should balance each other out, or they should be equal. If the anti-clockwise moment is greater than the clockwise moment, then it means that the object is not going to be balanced, but it is going to tilt anti-clockwise. Similarly, if the clockwise moment is greater, then the object is going to tilt clockwise. All right, so that's why if you have an object in equilibrium, both the anti-clockwise and the clockwise moments, they should sum up to be the same thing. Another condition that must be in place for an object to be in equilibrium is that the sum of the forces that act in one direction must be equal to the sum of the forces acting in the opposite direction. So here we have two downward forces. If the object is to be balanced, then it means that the reaction force that is acting from the pivot should be equal to the two downward forces as well as the weight of the plank itself in order for it to be balanced. Any questions so far?
No, miss.
All right. So another thing that is important for you to note is that the principle of moments allows us to have different types of levers, and levers work on the principle of moments. You have what we call, well, there are three classes of levers. There are first class levers, and these are the types where you have the pivot or the fulcrum is in between the effort and the load. So we can think of examples being like a seesaw, which is very common, or crowbars. The scissors are also examples of first class levers. Now, second class levers, you have the fulcrum or the pivot at one end, and the load is at the other end, meaning that the effort is in the middle. All right. Sorry, the effort is in the force that is applied as well as the fulcrum. Both of those are at either end, and the weight or the load that is being lifted is in the middle. So, for instance, wheelbarrows, doors, bottle openers, etc., those are second class levers. Third class levers are those in which the fulcrum is at one end, the the effort is in the middle, and the load is on the opposite end. So a mop or a broom or a fishing rod, those are examples of third class levers. All right. Now, we should also be comfortable in determining the location of the center of gravity of a body. Now, the center of gravity of a body is basically an average position for where the weight acts. So when we have what we call a uniform body, then the weight acts in the geometric center of the object. If we have something that is irregularly shaped, then we would have to experimentally determine the location of the center of gravity, and we can do so by using the plumb line method. Now, a key thing to note is that the stability of an object is directly related to where the weight is and center of gravity. So if a body is pivoted or supported at its center of gravity without any other forces acting on it, then it is going to be balanced or stable. All right. Any questions?
No, miss.
Okay. So we're going to be moving on to the worked question. This is from the January 2017 paper, question 3. Now they gave a passage with 4 blank spaces and you're asked to fill in the blanks. So the dash of moments states that when a body is in equilibrium, the sum of the dash about any dash is equal to the sum of the dash about the same dash. Okay? So we can simply fill in the blanks. It would be 1 mark per blank. So this first one here is principle. So it's the principle of moments states that when a body is in equilibrium, the sum of the clockwise moments about any point, or if you have pivot, that's fine, is equal to the sum of the anti-clockwise moments about the same point. Of course, if you had anti-clockwise first and clockwise after, it would be the same thing. All right. So it's just a statement of the principle of moments, which you should know. Now, the next part, you're asked to identify 2 situations in which a force will result in a turning effect. 2 marks, so it would be 1 mark per situation. Now, as we were mentioning earlier, you could state the use of any of the types of levers. So you could say using scissors or lifting a wheelbarrow, opening or closing a door, or loosening a nut with a crowbar. Any 2 of those situations could be stated. So I have a few of them here. Using a spanner to rotate a nut. You could be pushing or pulling a doorknob to open or close a door. Another example is in removing a bottle cork, also in pushing a swing and lifting a wheelbarrow. So any 2 situations that you can think of in which you have a turning effect, then you would just write those 2. Any questions?
Miss, would opening a security gate to be one?
Opening a security gate?
Yeah.
Yes, sure.
Okay.
Okay. All right. So the next part of the question, we have a figure that shows 2 boys, Kyle and Keon, balanced on a seesaw. Kyle has a weight of 500 newtons. Keon's weight is 300 newtons. You're told that the seesaw is made of a uniform plank of weight 800 newtons and it is 4 meters long, pivoted at its center. All right, so Keon's weight would be acting downwards, as would Kyle's weight. Keon's weight is 300 newtons. Kyle's weight is 500 newtons. Now, by taking moments about the pivot, you're asked to calculate the distance x that Keon must fit from the pivot in order to balance the plank if Kyle sits 1 meter from one end of the plank. All right. Now note that the question specifically tells us to take moments about the pivot. So we should remember that based on the principle of moments, in order for the plank to be balanced, then the sum of the anti-clockwise forces moments, must be equal to the sum of the clockwise moments. So what we need to do is to just apply the principle of moments, and then we would solve for the missing distance, which is x. Right? So bear in mind that the plank is 4 meters long and it is pivoted at the center. All right. So Kyle is applying a clockwise moment to the plank. So if you want to determine his distance, have to bear in mind that the distance that you use, it must be from the pivot and not from the end of the plank. So if the length of the plank is 4 meters and the pivot is at the center, it means that between the pivot to where Kyle is sitting is going to be 2 meters. So the distance from not to where Kyle is sitting, to the end of the plank, sorry. So the distance from the pivot to the end would be 2 meters. Kyle is sitting 1 meter from the end, which means that his distance would be 1 meter from the pivot. Right? So this distance would be 2 meters, and Kyle is seated 1 meter from the end, which means that he would be 1 meter away from the pivot. Right? So we can use that information as well as Keon's weight. Keon is to the left of the pivot, so it means that his weight would be supplying an anti-clockwise moment. We don't know the distance, which is what we're solving for. So when we take moments about the pivot, Kyle's clockwise moment times his distance would give, clockwise force times the distance would give 500 Newton meters, and Keon, his weight is 300 newtons, and we need to find the distance x. So all we need to do is divide both sides of the equation by 300 newtons, and that would give us a distance of 1.7 meters from the pivot. All right. All right. If balanced, you're asked to calculate the reaction force at the pivot. Now, the reaction force would be an upward force, and we know that Keon's weight as well as Kyle's weight would be acting downwards, and the weight of the plank is given as 800 newtons. Now, based on the second condition for equilibrium, the sum of the forces acting in one direction must be equal to the sum of the forces acting in the opposite direction. So the sum of the upward forces, well, in this case, we only have one, which is the reaction force, must be equal to the sum of the downward forces. So it means therefore that R, the reaction force, would be equal to 300 newtons plus 800 newtons plus 500 newtons, which is 1,600 newtons. All right. Everybody is okay so far?
Yes, miss.
Yes, miss.
Okay. All right. Finally, we are asked what is the moment of the reaction force about the pivot for 1 mark. Now remember that we said that moments are calculated by multiplying the force times the perpendicular distance from the pivot. Now the reaction force is directly above the pivot. That's where the object is being supported. So it means that the perpendicular distance from the pivot is equal to 0. Anything multiplied by 0 is equal to 0. So it means that the reaction force would not produce any turning about the pivot. So the moment is 0 Newton meters. All right. So are there any questions before we move on?
No questions, miss.
All right. So that's basically it for moments. So we're going to be moving on to the next topic, which is temperature. All right. Is Mr. Campbell, are you here?
Yes. My internet is very unstable. So let me try and see if, how much I can do here.
All right.
All right, so for temperature, you are to know the difference between heat and temperature and what temperature is. Now, temperature can be defined in a number of ways. And one such way is that it is a measure of the average kinetic energy of the molecules in a substance. Normally, for a simple definition, we also say that it is how hot or cold something is. All right. But this definition gives us a deeper understanding of temperature. It's a measure of the average kinetic energy, which is important in further studies on temperature. All right. When two objects are of different temperatures, then energy will move from the hotter one to the colder one, and that energy is called heat. So whenever a substance has an increase in temperature, it means that it absorbed heat, while if a substance decreases in temperature, it means that it would have lost heat. So these are some of the things that you should know. And what you should be able to do, differentiate between heat and temperature, and relate the temperature of a body to the kinetic energy of the molecules, relating the temperature to the direction of net thermal energy transfer. So all of this that you should be able to do would have been embedded in this section here. All right, we also deal with the thermometric properties, and these are physical properties which change with temperature. So we know that the volume of a liquid, for example, increases when temperature increases. We know that the volume of a solid also increases when the temperature increases. And we know that the electromotive force between between one pair of different wires also increase. So these properties can be used as a basis for measuring temperature. And so we find them being used in different types of thermometers. So in a liquid in glass thermometer, you would see the expansion of a liquid, which is either mercury or alcohol. In the bimetallic thermometer, it is it is due to the expansion of the metals. And in the thermocouple thermometer, it would be the temperature would be a reflection of the electromotive force, right? So we have different thermometers for, using different properties of matter. All right. So once you know these thermometric properties, you should be able to identify properties which change with temperature. All right. You are to also know about the fixed points on the Celsius scale. You have a lower fixed point, which is the temperature of pure melting ice at standard pressure. And this is designated 0 degrees Celsius, while the upper fixed point is the temperature of steam above water boiling at standard pressure. And this is designated 100 degrees Celsius. So this is what you should be able to define the fixed points. All right, our question comes from January 2016. So this is a recent paper, question 3. And the first part gives us a table which compares the design features of 3 types of thermometers. So what you're to do is to fill in the blank spaces here. The first type of thermometer is a mercury in glass laboratory thermometer. And the design feature that they're asking or they're referring to is a narrow bore. And so you must state the reason, the correct reason for the narrow bore. All right. So the narrow bore, the bore is actually the internal diameter, right? So the space inside of the capillary tube that keeps the mercury or the alcohol. That is what they're talking about, the bore. All right. So the narrower the bore, the greater the sensitivity of the thermometer, right? Because it will be able to show a small change easier when the bore is narrow. All right. Now the second thermometer is not given, but you are told the design feature is a constriction in the bore, and the reason is for retaining a measured temperature. So the only thermometer with a constriction in the bore would be the mercury in glass clinical thermometer. All right. So this is basically 2 thermometers using the same principle, but one has a constriction in the bore. Third one now is a thermocouple, and the ability to measure rapidly changing temperatures is the reason for the design feature. So you are to find the design feature which matches this reason. And the design feature would be very small wire junctions. Now, for this, it means that you have to be very knowledgeable about the different thermometers. And the small wire junctions mean that the sensor, which is the junction, does not need a lot of heat, all right, for it to change temperature, because it's small. The smaller it is, the less heat it requires for a particular temperature change. So because it has a very small wire junction, then it can measure rapidly changing temperatures. All right, next part of the question.
Excuse
Find
me.
the upper and go again.
So if they said for the design feature, a junction of small mass, would that be the same as like the thermocouple?
Yes.
Okay.
Yeah. All right. Define the upper and lower fixed points on the Celsius temperature scale. So remember back in the table, we had talked about the upper and lower fixed points. And so we can define the upper fixed point. That's the temperature of the steam above water boiling at normal atmospheric pressure. So that's 1 mark for defining, and 1 mark for the value, which is 100 degrees Celsius. The lower fixed point. So this is the temperature of pure melting ice, and the value is 0 degrees Celsius. 1 mark for the definition and 1 mark for the value. All right. Next. All right, so this is part C, same question paper. All right, figure 2, that's the diagram over here. So we see a pressure gauge connected to a vessel here, which contains a gas, and that vessel is surrounded by a fluid, and a thermometer is placed in the fluid. Everything is being heated. So, this question is having to do with some gas law. All right, so what you are to find, however, is the Kelvin temperature. So you are to convert the Celsius temperatures given to Kelvin. And to do that, we simply add 273. All right, so temperature in Kelvin is equal to the Celsius temperature plus 273. You're going to add 273 to all of these to get your answers in the final column here. All right, so 35 plus 273 is 308. 63 plus 273, 336. And 91 plus 273, that's 364. So pretty easy, 3 marks here. All right, this question now is from the receipt of 2014. All right, state the physical property that varies with temperature in each of the following thermometers. So we have the laboratory thermometer, and we have the thermocouple. So in the laboratory thermometer, we know that it is the volume of a liquid that changes when the temperature changes. All right, so that is used to indicate the temperature. And then for the thermocouple, it is the EMF. EMF means electromotive force. So the EMF changes, the EMF between the end of 2 wires, that will change whenever the temperature changes. Right? So just simply stating the answers here. Next question.
I think that's it.
Oh, that's it?
Yeah.
Okay, so there's the gas laws
Yeah.
would be the next topic that we look at.
Mhm.
You're doing this on Ms. Rose.
All right, sure.
Excuse me, sir. You can go back to the last slide, please. Okay, thank you.
All right. So also related to thermal physics and the kinetic theory is the gas laws. And of course, you should be familiar with the fact that the gas laws pretty much explain the relationship that exists among the variables of pressure, volume, and temperature, absolute temperature that is, for a fixed mass of gas. Or in some books or so, you would see them tell you that it's the number of molecules, means that the mass is fixed. All right. So you should be able to relate the graphs of pressure or volume against temperature to the establishment of the Kelvin temperature scale. There is a slide coming up with the graphs. We should also be able to use the relationship between the Kelvin and Celsius temperature scales. We touched on that a little earlier, where we did some conversion between temperatures in Celsius and we converted to Kelvin. You should also be able to apply the gas laws to solve problems. Each of the laws is stated below or on the slide to the left. For each of the laws, basically, one of the variables other than the mass is kept constant. So for Boyle's law, it is the temperature that is constant, and basically the pressure is inversely proportional to volume, which means that if the pressure is increased, then the volume decreases. And it's in such a way that if the pressure is doubled, for instance, then the volume is halved. And this is if the temperature is kept constant. Now, in terms of the kinetic theory of matter, you can envision that if you have a, a gas that is held in a fixed container, if you keep the temperature constant and you apply pressure to that gas, meaning that you squeeze down on the container, then the space that the gas has to move about in would decrease, all right? So that's a simple way to look at it. If the container is somehow expanded, then it would reflect in a decrease in the pressure because you would have fewer collisions of the molecules with the walls of the container. All right. With Charles' law, it is the pressure that is kept constant. So the temperature is changed and the volume is changed. Now, if you have a gas and you increase the temperature, then you should also expect the volume to increase. And we would observe that daily, where we know that if a gas is heated, then it expands, which means that the volume increases. So volume is directly proportional to the absolute temperature at constant pressure. For the pressure law, the volume is kept constant, and if the temperature is increased, then the pressure will also increase, and it will increase by the same factor. So if you increase the temperature of a gas, that is going to increase the kinetic energy of the molecule, so they will move faster. Thus, there will be more frequent collisions of those molecules with each other as well as with the walls of the container that they are in, and that constitutes an increase in pressure. The general gas law or the general gas equation is what is applied when all three variables change and the only thing that is kept constant is the mass of the gas. So basically it states that for a fixed mass of gas, if there is a change in the pressure and the temperature, the pressure is directly proportional to the temperature and inversely proportional to the volume. All right. Now, another thing about the general gas equation is that you can pretty much use this equation to get either of Boyle's, Charles, or the pressure law by just covering up the variable that is constant in each case. Okay. So I think we have a little bit of time. So for instance, if notice that for the general gas law, basically you'd say P1 times V1 all upon T1 is equal to P2 times V2 all upon T2. So if you want to, if you're told that there is constant pressure, then you can just simply cover up P1 and P2 and you'd end up with Charles' law, which is V1 over T1 equals V2 over T2. If the volume is constant, then you end up with P1 over T1 equals P2 over T2, which is the pressure law. And if the temperature is constant, then you would cover T1 and T2, and you end up with P1 times V1 equals P2 times V2, which is Boyle's law. All right, so that may come in handy if you're in a pinch. All right, so we're gonna be looking at the graphs of Charles and the pressure law, sorry. Now note that, of course, when we work problems involving the gas laws, the temperatures must be expressed in Kelvin. And this is because if, for instance, if we're looking at Charles' law and you plot a graph of volume against temperature in degrees Celsius, you notice that the line that you get does not show direct proportion. All right. Now, if you trace the line backwards, then you'd realize that where the volume is 0, whatever unit of volume you're using, cubic meters or cubic centimeters, etc., then the temperature correspond to approximately negative 273 degrees Celsius. And if we were to use absolute temperature, then that would correspond to 0 Kelvin. All right, so this is why we have to use the temperatures in Kelvin so that it will actually constitute or correlate with what the law states. Same thing applies for the pressure law. If you plot a graph of pressure against temperature in degrees Celsius, the line does not show direct proportion, but if you trace backwards to negative 2 to 0 pascals or whatever your unit of pressure is, then it would correspond to negative 273 degrees Celsius, which is equal to 0 Kelvin. Okay. Okay, so we are gonna be looking at a worked question. This is from the May-June 2015 paper, question 5. And coincidentally, it's asking us to describe how you could use the graph of volume versus temperature in degrees Celsius of a gas to derive the Kelvin scale of temperature. And this is 4 marks. All right. Now, the key word here is describe, which means that you need to give a substantial statement, and also notice that it carries a lot of marks. So you need to explain properly what it is that you are going to say. Right. So it's helpful if you have a sketch that you can refer to. So volume versus temperature in degrees Celsius. What we have here, remember that whenever the volume of a gas is 0, then the temperature is known as absolute 0, which is 0 Kelvin. So if you plot a graph of volume against temperature in degrees Celsius, then you can extrapolate the line to where the y coordinate, which is the volume, is 0, and the corresponding x value, which is the temperature, will be the equivalent of 0 Kelvin, but in degrees Celsius. Okay. All right. Now, based on that, you're asked to state the mathematical relationship between the Kelvin and Celsius temperature scales. You can just write a simple mathematical equation. You can write that the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273, or you could write that the temperature in degrees Celsius is equal to the Kelvin temperature minus 273. All right. So we're moving on to the next part of the question. A piston traps a mass of gas in a cylinder. At 25 degrees Celsius, pressure of the gas is 5 atmospheres and the volume is 50 milliliters. You're asked to calculate the volume of the gas if the pressure drops to 1 atmosphere at constant temperature. All right, so it's always helpful to write down the quantities that we have and the ones that we're going to use. Since the temperature is constant, we don't need to write it down at this point. So the first, or the initial pressure, is 5 atmospheres. The final pressure is 1 atmosphere, and the volume initially is 50 milliliters. We want to calculate the final volume of the gas. Now remember that at constant temperature, Boyle's law must be applied. All right. And remember that the pressure and the volume are inversely proportional to each other. So we can multiply our initial pressure times our initial volume, and that should be equal to the final pressure multiplied by the final volume. So we can just substitute our values. So P1 is 5 atmospheres, V1 is 50 milliliters, P2 is 1 atmosphere, and we want to find V2. So of course, we can simplify this side of the equation. 5 times 50 is 250, and we can write our unit here. You don't have to, but you can. And you can't simplify this side any further because we still have this unknown. So to find V2, we divide both sides of the equation by the final pressure 1 atmosphere, and that would give us 250 divided by 1, and the atmospheres would cancel, and we are left with a unit of milliliters. So our final volume is 250 milliliters. So the final part of the question asks us to calculate the final pressure of the gas if the piston is reset and the gas returns to its initial pressure and volume, with the volume now being fixed and the temperature increasing to 60 degrees Celsius. All right. Now notice that in this case, the volume is now fixed and the temperature is going to increase from 25 degrees Celsius to 60 degrees Celsius. Now realize that we are now working with pressure law, and because of the fact that the pressure law only applies when the temperature is given in Kelvin, we need to change our Celsius temperatures to Kelvin by adding 273. All right. So our initial temperature would be 25 degrees Celsius, which is equivalent to 298 Kelvin, and our final temperature is 60 degrees Celsius, which is equivalent to 333 Kelvin. Now, according to the pressure law, the relationship that exists between the pressure and the temperature is one of direct proportion. So it means P1 over T1 is equal to P2 over T2, and we just fill in our values. Remember, we use the Kelvin temperatures, and we solve for the final pressure of the gas, which is P2. All right. So 5 atmospheres divided by 298 Kelvin is equal to P2 divided by 333 Kelvin. So we can solve for P2 by multiplying 5 atmospheres by 333 Kelvin and dividing by 298 Kelvin. When we work this out, it will give us 5.6 atmospheres. All right. Are there any questions?
No, miss.
All right. So, Mr. Campbell, it's over to you again. You can do the wrapping up. I'm not sure if Mr. Campbell is having difficulties. Right. So basically that's really it for what we have planned for this session. So if you have any questions or queries, we can take those now before we end.
Miss, you can go over about question one in the last one.
Question one, the graph one.
No, miss. In the last question, you just did the first part.
Okay. Me. Yeah, this one. All right. So what we're saying is
No, miss,
that,
the one after that. Sorry.
oh, the
It's
one
the
with
one
the
after
working
that.
out.
Yes, miss.
Okay. All right, cool. All right. So we have a piston that traps a mass of gas in a cylinder. It's originally at a temperature of 25 degrees Celsius, and the pressure of the gas is 5 atmospheres. That's our initial pressure. And the volume is 50 milliliters. That's the initial volume. So the first thing that you're asked to calculate is the volume of the gas if the pressure drops to 1 atmosphere at constant temperature. Right? So because the temperature is being kept constant, you can basically ignore the temperature for this part of the question. You're only focused on the pressure, initial pressure of 5 atmospheres, the initial volume, and the question gives us the final volume, which would be P2. So basically want to find V2. So V2 would be our unknown. All right. Following?
Yes, miss.
All right. Now, when the temperature is constant, then the volume and the pressure changing would indicate that we would have to apply Boyle's law. Now, Boyle's law states that the pressure is inversely proportional to the volume. So you would state that as P1 times V1 equals P2 times V2. All right. So this is for Boyle's law. So all we would need to do, therefore, is plug in the values of the quantities that we do know. We know the initial pressure is 5 atmospheres. The initial volume is 50 milliliters. And we know that the final pressure is 1 atmosphere. So V2 is actually what we are trying to solve for. All right. So if we plug in the values here, we can simplify this side of the equation because we don't have any unknowns. 5 times 50 is 250. If you want to work with the units straight through, then you can multiply the atmosphere times milliliters. And, you know, when you multiply two units, you can just join them together. All right.
Yes, miss.
All right. Now on the right side of the equation, we can't simplify this any further because V2 is unknown. So we just apply some mathematics here where the what we have here is a product between 1 atmosphere and V2. So if we want to make V2 the subject or to find the value of V2, we have to use the inverse operation, which is division. So we divide both sides of the equation by 1 atmosphere. All right, so if we divide this side by 1 atmosphere, then 1 atmosphere would cancel 1 atmosphere and we'd be left with V2 on this side. And 1 atmosphere into 250 atmosphere milliliters would be 250, and the atmospheres would cancel, leaving us with milliliters.
Okay, miss.
All right. Now, of course, you can always transpose the equation before you plug the values in. If it's easier for you to do it that way, then no problem. You could say V2 is equal to P1 times V1 divided by P2, and then you plug in the values afterwards, you get the same thing. So it depends on how you are comfortable with working the question. All right. Are there any other questions? All right. Mr. Campbell, are you here?
Yes, I'm here.
All right. You can do the wrapping up.
So this is the last question, right?
Yeah, we finished the last one.
Okay. All right. So I want to just thank everyone for participating, and I hope it was helpful. We have scheduled 3 more sessions, so we should have the next session next week. All right, so we'll be doing the other topics, some of the other topics next week, and you know, just prepare yourselves and come again next week. Thanks, Miss Rose, for helping out.
You're welcome.
All right, so guys, if you have any questions, you may type them in the chat, or if you want to speak. Any special requests or so, you can let us know.
No questions, sir.
All right, it seems like somebody had a question.
No, sir.
Okay. All right, it seems like everybody is fine, so we can stop here, and then next week we continue. Okay, Christopher is asking if there are any more questions on moments. Yeah, we should be able to find more, but because of the time constraints, you know, we have 2 hours, we have to cover a lot of topics. So we didn't try to put as much as possible, but we'll see if we can work one more next week. Okay. Any other questions? All right. So see you guys next week then for the second session. You can finish off, Ms. Rose.
All right. So have a good evening and a good week, everyone. All the best, and we'll see you on Sunday at 5.